Okay, let's look at an AP question of the day. It is no calculator. So pause it, read the question, see what you get, come back for the explanation. The function f is twice differentiable, so that means we can take the second derivative. They give us values of the original function at 3, its value is 8. Of the derivative at 3, it's 22, and the second derivative of 3 is 18. What is the value of the approximation of f of 2.9 using the line tangent to the graph of f at x equals 3? Something that you need to automatically do is mark out this information right here. They're really just trying to throw you off. When you're doing tangent line approximations, all you need is a point on the original function, an x and a y. So that's right here. Here's your x, here's your y. And you need the slope because you're writing a tangent line. So the slope at a point, that comes from the derivative. So here you go. The slope is going to be 22. What is the value of the approximation of f of 2.9? Okay, this number should always be close to the x value that you're finding the derivative at. That's the whole purpose. It's an approximation, so it needs to be close to it. So we need to write the equation of our tangent line to begin with. So we've got y minus 8 is equal to the slope, 22, times x minus 3. Okay, and then we need to plug it in. Okay, plug in 2.9. 2.9 minus 3 is negative 0.1. So when we multiply 22 by negative 0.1, that's going to give us negative 2.2. So then when we add 8 to both sides, really we're subtracting 2.2 from 8. So when we subtract 2, we get 6. Take 2.2 away from that, we get 5.8 for the approximation. Now that could also be called a local linearization. A local linearization, it's the exact same thing, okay? You are focusing in on one part of the function and you're using a tangent line to approximate instead of finding the actual value of the function. All right, so let's look at our next topic. We're going to look at the derivatives of inverse functions. Okay, the derivatives of inverse functions. They love, you see on the release test that I've seen, there's usually 1 or 2 questions about this. So pretty much it's just, we're going to get a formula. We got to know how to be able to use that formula. So here's our derivative of an inverse function. If we have a function f that's differentiable on an interval I, okay, that's pretty much the basic thing that we've been seeing in all of our theorems. If f has an inverse, we're going to call it g, then g is differentiable. Okay, so if the original function, you can take the derivative of it, you can also take the derivative of its inverse. Okay, and as long as f prime of g of x does not equal 0, here is the formula, so to speak, for the derivative of the inverse. So g is the inverse function. G is the inverse function. So the derivative of g, the derivative of the inverse, is equal to 1 over f prime of g of x, as long as f prime of g of x is not equal to 0, because obviously we're not allowed to divide by 0. Now, you're probably wondering, well, where on earth did that come from? Well, let's look at part of the definition of inverse functions. Do you remember from Math 3 or hopefully pre-calculus, you learned that if 2 functions are inverses, that is only true if you compose them and their composition equals x. Okay, so if f and g are inverses, then f of g of x equals x. That is the definition of inverse functions. So let's take the derivative of that expression right there. Okay, let's take the derivative of that expression. So the left side here requires the chain rule. So the derivative is f prime of g of x times g prime of x. The derivative of the right side, the derivative of x, is simply 1. So if we are looking for the derivative of the inverse, g being the inverse, then to get that by itself, we're just going to simply divide by 1. So here's a neat thing. If you forget this definition or this formula, if you can remember that, you can very, very easily figure it out. Okay, you can very, very easily figure it out. Just remembering that g of x is, I don't like using different letters because I get them mixed up, but you will see them use it a lot. But the important thing is that g of x is the inverse of f. Okay, so you could also write that as f inverse of x. Okay, so that's why, but this is the formula that we're going to be using. Let's look at some examples here. So our first example says, here's our function, f of x equals 1/4 x cubed plus x minus 1. We are told that f of 2 equals 3. Okay, f of 2 equals 3. So that is the original. Okay, that is the original, 2, 3. We'll just say f of x, okay? Or you can write original. You're going to see why I'm doing this here in a second. Okay, so the first part says, what is the value of f inverse of x, the inverse function, when x equals 3? When x equals 3. Well, remember what inverse functions mean. Okay, if we have the point 2,3 on the original function, then we have the point 3,2 on the inverse. Okay, if 2,3 is a point in our original function, then the point 3,2 is the inverse, so f inverse of 3 is equal to 2. Now the reason why I do that, why there is that part of the question in here, is because they're going to ask you what is the value of f inverse, the derivative of f inverse of x, when x equals 3. Now, here's the reason why you have to be given f of 2 equals 3. Because we cannot find a definition for the derivative of that, or for the inverse of that function. Okay, remember the protocol for finding the inverse of a function? We switch x and y, and we try and solve for y. Well, you can certainly try, but you can't separate those y's right there. You cannot separate those y's, so we cannot find an explicit rule for the inverse of this function. So the only way to find the value of the derivative of the inverse is to use our rule, okay? Is to use our rule. So our rule says the derivative of the inverse is equal to 1 over f prime, the derivative of the original of the inverse of x. So this is saying when x equals 3, so we are looking for f inverse prime of 3. I said that in the wrong order, f prime of the inverse of 3. Okay, so that's 1 over f prime of f inverse of 3. We know f inverse of 3. That came from part A. F inverse of 3 is 2. So we need to find f prime of 2. Well, we may not be able to find the inverse of f, but we can find the derivative of f. F prime of x is equal to 3/4 x squared plus 1. Just simple power rules there. So f prime of 2 is equal to 3 over 4 times 2 squared plus 1. Well, 2 squared over 4, that's going to be 1, so 3 plus 1 is 4. So this is equal to 1/4. It's equal to 1/4. You may need to go back and rewatch that example to fully grasp it. Okay, so let's use this whole idea to find the derivative of the inverse tangent function. Now, a lot of times they like to use this notation for the inverse tangent. They use arc tangent. And the reason why is because if they use the -1 exponent for the inverse, a lot of people want to just apply the power rule to that. Okay, but you can't apply the power rule to that because that -1 is not an exponent. The -1 there is indicating the inverse tangent function. So the button on your calculator is tangent to the -1. Or yeah, I think so. Or maybe on the fancy calculator, it does say arctangent. But anyways, moral of the story, those are the same things. Okay, arctangent and the inverse tangent function are the same thing. But you cannot use the power rule to find the derivative. Okay, it doesn't work. What we are going to use is we're going to use the definition of the inverse derivative. So we are trying to find the derivative of the arctangent. So our function, f of x, is arctangent of x. Our function is the arctangent of x. Okay. Now the inverse of the arctangent is tangent. Okay, the inverse of the arctangent is tangent because we're talking about the inverse tangent function. So the inverse of the inverse is the original. Okay. Hopefully that kind of makes sense. Okay. The inverse of the inverse tangent is just tangent. All right. So let's apply this. Okay. Let's apply this using our rule here. Okay. So we're trying to find the derivative of the inverse function. So that's 1 over, and I think I've got my f and g mixed up here, okay? But that's 1 over the derivative. I really do think I have my f and g mixed up. Yeah. Let me use this notation. Instead of g of x, let me use f inverse. I like that better. Okay. Okay. So f inverse is the tangent of x. No, sorry. I have the original and the inverse mixed up. Let's just start again. Sorry. All right, let's try this again. The original function is the tangent of x. The inverse function, what we're trying to find the derivative of, is the arctangent of x. I apologize. All right, so let's try again. The derivative of the inverse is equal to 1 over the derivative composed with the inverse. All right, so our inverse function is the arctangent of x. Now, what is the derivative of f? Okay, if f is equal to the tangent of x, then the derivative of tangent is secant squared. Now, secant squared here doesn't do us a whole lot of good, but what will do us some good is that secant squared, do you remember those trig identities, those Pythagorean identities? Secant squared is equal to the tangent squared plus 1. Okay, it's a Pythagorean identity. So, let's plug this in. 1 over the derivative is tangent squared of x. The derivative is tangent squared of x. So we are going to replace x with the arctangent, okay, because we're plugging that into the derivative. That expression is squared, and we're adding 1. Okay, we took the derivative here, we're plugging it in, and then we're plugging the arctangent into the derivative. Now, tangent and arctangent are opposite. They're inverses. Okay, they are inverses. So when you plug the arctangent into the tangent, they're inverses, so they undo each other. So all you're left with is the x. And this is the derivative of the inverse tangent function. Okay, so the derivative with respect to x of the arctangent, or the inverse tangent function of x, is equal to 1 over x squared plus 1. Now, this is not something that is very heavily tested. Okay, it is not very heavily tested. Sometimes it shows up. But my little note in my teacher's edition here says that the inverse sine and inverse tangent functions are the most likely topics. The inverse sine and the inverse tangent functions are the most likely topics. So here are the derivatives of the inverse trig functions: arcsine, arccosine, arctangent. You also have arccosecant, arcsecant, and arccotangent. But again, here will be the focus: arcsine, arctangent, inverse sine, inverse tangent. So if you learn those, then you're going to be good. Now, you may be saying, well, that looks a little bit different than what we just got. It is, okay, because most of the time it's not just going to be the inverse sine of x, okay? It's going to have some kind of chain rule involved. So that's where the u comes into play. And you know, anytime you use the chain rule, you multiply by the derivative of what's inside. So that's where the u primes come from in the numerators of all of these, okay? That's where the u primes come from. And notice the cosine, its derivative is negative, just like the derivative of cosine is negative sine. Cosecant, cotangent, remember all the cos were negative. All the cos were negative with the regular derivatives. Same thing applies here, so when you're trying to learn them. But again, the focus is on the sine and the tangent. If you memorize those, that's what I would love for you to know. But I'm going to ask you to do some problems here involving them all. So just keep these formulas handy, but memorize the arcsine and the arctangent. Okay, so let's use these. Okay, let's make sure that we know how to use these rules. Okay, if we're taking the derivative with respect to x of the arcsine of 2x. Okay, so our rule for the arcsine says it's u prime. This part is the u, so the derivative of 2x is 2 over the square root of 1 minus u squared. So 2x squared. We got to do some simplifying here. We square the 2 and we square the x. And that's it. We can't simplify anything else. You cannot simplify that square root because of that minus under there. I know it's really, really tempting, but you can't. Okay, even though those are perfect squares, because that minus can't go any further. Okay, let's look at B. The arctangent of 3x. The arctangent of 3x. So again, arctangent is u prime. This is u. So the derivative of 3x is 3 over 1 plus u squared. Whoops, 3x squared. So that's 3 over 1 plus 9x squared. Again, no more simplifying, okay? All three of those constants would have to be divisible by 3 to simplify. Okay, arcsine square root of x. The arcsine of the square root of x. So square root of x, again, is our u. So it's u prime. What's the derivative of the square root of x? 1/2 x to the negative 1/2. We'll clean it up here in a second. Over the square root of 1 minus u squared, so the square root of x squared. Now, what we can do is the 2 right here. It can go into the denominator, okay? Because if you think about it, it's flipping and multiplying. It's going to end up in the denominator. The x to the negative 1/2, the negative exponent, get rid of it. That goes in the denominator as well. So we've got the square root of x. So we don't have anything left in the numerator. And in the denominator, we've got 1 minus, well, when you square the square root, you just are left with the x. And when you're multiplying two square roots, you can just multiply what's under the square root. So we've got x minus x squared. Okay, and let's look at D, the derivative for the arcsecant, and we're throwing some exponentials in there just for the heck of it, because we need to make sure we practice those. Sorry, I'm trying to alternate colors, OCD like that. All right, so arcsecant, our rule says u prime, so what's the derivative of e to the 2x? It is itself times the derivative of its exponent, so e to the 2x times 2, over the absolute value of u, which is e to the 2x, times the square root of u squared, e to the 2x squared, minus 1. So let's clean this up a bit. We write that as 2e to the 2x over, we really don't need those absolute values around e to the 2x because e to the 2x is always positive. So we can drop the absolute value bars. When we raise power to a power, we multiply, so that's e to the 4x. And we can cancel those e to the 2x's. So we have 2 over the square root of e to the 4x minus 1.